All right. So thank you very much. My name is Peter Clausen. I'm from the company Dassault Systèmes. I'm here with my colleague, Pascal Hebrard.
So yes, my name is Pascal Hebrard. I'm also working at Dassault Systèmes for CATIA R&D.
Yep. So I am from more the simulation side of things, and we wanted to have a little bit of another take on the computational design, which many people have been working on for decades. So I'm originally from Ole Sigmund's team, graduated back in 2005. And we want to kind of promote computational design also for conventional manufacturing, not only additive, right? And that's kind of like the theme in this talk. So the outline is we're going to give a short presentation into what we call ModSim on the 3D experience. Then very shortly show what is possible today in additive manufacturing on the 3D experience and virtual prototyping and that stuff. Then the main part of this talk is talking about conventional design, computational design for conventional manufacturing on 3D experience. And we're just going to basically take two parts, so a sheet metal part and a casted part, and have a look how that actually is going on from a computational design point of view. And at the end, a conclusion and a small fun note. Our legacy, so Dassault Systèmes started back in the 80s. Actually, Abacus, which is a finite element solver, started in 1978. So that's the same year I was born. So we're talking about technology with quite a bit of legacy here, and not like some of the startups that are probably only a decade or two old. Start out 3D design, then digital mock-up, where you basically have not just one part, but assembly of parts, like an airplane or a car or something. Then 3D PLM, where it's not parts only, but also processes, so product lifecycle management. Then we're moving into the 3D experience platform in the 2012s. So here's a picture of a city where you're trying to kind of virtualize, I think it's Singapore, yeah, it is. Singapore is like a virtual prototype of Singapore. And we're moving into like virtual twin experience for humans. So we bought Medidata back in 2019 or something. And we're moving towards the virtual twin experience for a sustainable world. I'm not sure what that means, but I hope this part is actually on the way to that. The ModSim technology is basically just combining modeling and simulation together in a common data model. And that's in a single user experience for the 3D experience platform. So it's basically for all of physics that we're able to do in our simulation. We're using mainly CATIA CAD and simulation done by Simulia, so that would be Abacus or Tosca, so that's all what's running here underneath. And the basis of this technology is that the old workflow is basically you're starting with some design, and then you usually change into other products to do meshing, and then you do execution, and then you post-processing, and often that can even be multiple products at some companies. And that actually takes quite a lot of time to do this whole process. So the goal of the ModSim experience is you start with a CAD up here, and you select your CAD. Then you go into the CAE process. You do all of this, but all of that is on the 3D experience. And basically, when you go back, let's say you're doing optimization, so you do a CAE update. That forces then some changes on the CAD, and then you can validate, and this loop goes on. And we target to reduce the time to simulation. So now I'll give the word to Pascal on additive.
So we started generative design in the context of additive manufacturing and 3D printing because of the shape that are produced by the topology optimization. So we started by launching topology optimization and giving some very nice shape, but very complicated to produce except by additive manufacturing, on which, by the way, we have the full workflow, including lattice structure creation, with in the middle some images of the meshes with solid elements, shell elements, beam elements, as we saw this morning, but also with another brand from Dassault Systèmes, which is Delmia, all the setup and the manufacturing simulation until the printed part. But together with topology optimization or with other technique of optimization like shape optimization or bead optimization, we wanted and we saw a lot of advantages to use that technique in other domains, like Peter said, for more conventional manufacturing processes, like casting, like milling, or bead for sheet metal that we are going to show you now.
Thank you very much. So we're going to show these two examples. So it's basically computational design for conventional manufacturing. So I'm first going to show bead optimization. So it's basically just sheet metal model, and then a topology optimization of a solid part, which is casted. So let's say I'm in an automotive industry and I'm probably not producing one of or just one of the cars. This is just we call it blue car. It's like a generic car that we're using for internal testing. And I have some design of some part, and the eigenfrequency for that is too low. The first thing I do is I do a naive bead design. So hopefully you can see here there's some small beads here. That's a good choice, but the eigenfrequency does not change that much. So what can I do again? Well, let's run a bead optimization. I'm not going to go into much how that actually set up and work, but basically we're changing the positions of the nodes here. We're running the optimization. It takes like 20 minutes on a laptop, and we get this very curved design out of it. And actually here you see the optimized design is a subdivision surface, so it is a CAD part, but it's not parametric in the classical part, the classical sense of the word. So the question is now, how do I actually get a parametric sheet metal part out of this? Because that's often what my other colleagues in the manufacturing actually want. So Pascal, can you help me with that?
So we will now play a video that has been recorded from the tool I hope we will play the video. So it's just at speed 1, it has not been accelerated. So directly inside the optimization tool, we can launch a reconstruction, which is not to generate only a subdivision surface, but to automatically generate a CAD model, a CAD modelization of the bead optimization result.
And it should now run, but of course it doesn't run.
It used to run.
I don't know why it's not going. Now it's actually going.
Okay.
Sorry about that.
So we generate here a surface which is based on some ISO curve from the optimization. So you can choose your reference ISO curve. And then we use the sketcher capability from CATIA in order to convert this curve into several type of sketches inputs. We have several strategies. Here we are following a very complex geometry, but we can change that with several primitives, and afterwards we use all the CAD capability from the software. For example, with the sweep managing the draft angle, we could have had fillets, and we finally have a part which is made thanks to the result from the topology optimization, and which has a full CAD parametrization, so which is ready for design of experiment.
All right. So here are the result validation. So basically we have first the initial design, we have the, let's say, the naive design, we have the direct result, which is kind of wild and let's say bumpy. But then we have this really nice bead design. Actually, we added here also some fillets to make it look nice and almost manufacturable. There's probably going to be some manufacturing people who's going to say this is going to be really hard to manufacture. So that's definitely a discussion worth having. But just to showing you that there's a lot of possibilities here with conventional design as well. So that was bead optimization. Oh, and also I should probably mention that we're losing a couple of hertz in the eigenfrequency, which is quite typical. So when we're going from, let's say, the optimized design into the parametric version of it, we are going to lose something, but it's at least a lot better than our initial design and also much better than the naive design. All right, so the next one is this casted part. So this is basically just an engine mount. It's also a little bit of a generic model. You should imagine that on the end of this, there's like an electric engine, and this mount was designed by someone in the company, and we're looking at it, and we figure out it's not stiff enough. So what we do, well, we can just run topology optimization. We want it to be casted, right? So we have many manufacturing constraints in our software, so you can do ribs, different casting, and so on, maximum, minimum member size, symmetry, and so on and so forth. So here we're choosing this rib constraint. So what you have here is basically this topology optimization, again, ran quite quickly on a laptop, so only like 9 minutes, 10 minutes-ish. Probably should have used a much finer mesh to get finer ribs and stuff, but this is actually not the point of the talk. The point I want to make here is that since many years, actually 2016, I think we were one of the first companies to produce these advanced subdivision surfaces from a topology optimization, which is nice and cool, and it's a CAD surface. I can actually do stuff with that. However, it's not parametric in the sense of what we usually think about parametric. So again, Pascal, what do we do with this?
So same here, a video that I hope will launch correctly that time. So here, all the idea is first to set the constraint directly in the topology optimization, and then in the reconstruction afterwards to reuse the CAD capabilities from CATIA to create a new kind of CAD, which is not made of subdivision surface, but on classical modelization features like sketches. So here you see the same kind of methodology with strategy to approximate the ISO surface and some traditional feature like pockets or Boolean operation, just to provide a finished part to the end user that he can freely edit thanks to the CAD parametrization and all the parameters that are being automatically defined for him.
All right, good stuff. So now we have a parametric model, and we can now do validation, and a couple of points here to make. So we have the initial designs, about 5 kilos. The maximum displacement is 7 millimeters. So when we do the topology optimization, we're actually gaining a bit of mass. The reason for this, it's a little bit hard to see, but due to the big flat structure there, the subdivision surface is actually adding a little bit of mass on the whole middle section of the structure, which shouldn't be there. So that's why that thing is a bit heavier. When we then go into the reconstruction part, we are down at the good mass again, so we're below the initial mass, and we see that our displacement has decreased a lot. So the whole point of this talk was not to go into too much details about all the simulation and optimization stuff. In Dassault Systèmes, we can do much more complicated simulations and optimizations. We also have the capability to combine parametric optimization together with topology and others in single workflows. And we're working actually also together with the CST, who got acquired by Dassault Systems, to do electrical magnetic optimization on like electric drives and stuff like that. We don't have time to show all that, so unfortunately we are trying to stay within the time limits of today and get to the conclusion, which is, I hope I gave you just a little taste of what ModSim, so combining modeling and simulation in a single experience on a single platform, and that it's possible to do computational design, not only for additive, but very importantly, for conventional manufacturing, which is really essential for any big industries building, let's say, cars, planes, whatever, things with large numbers of parts. It's really important for the industrial applications to have end-to-end workflows. I think a lot of the colleagues from the other companies showed that as well. So in my mind, the result of an optimization is a new CAD, it's a new CAD geometry. It's not just a density field or an isosurface. It should be the thing that actually goes into your product, your car, your iPhone, whatever the thing is. And then I think non-parametric methods are really powerful. So topology, shape, bead, sizing, whatever, they can do a lot of cool stuff, but you need to have the right manufacturing constraints and need to have these CAD reconstruction methods to be able to use them in an industrial setting. And then at the last, I'm just going to give the word to Pascal for...
Yes, thank you. So I would like to end by 2 points. So first is to thank Duan for setting up the workshop, the conference here in this nice building from in Berlin, but also with a disclaimer. So this building has been built and designed by Frank Gehry, which is a user of CATIA since decades, and he used CATIA to design his building, also this one, but also the Guggenheim Museum in Bilbao or the Fondation Louis Vuitton in Paris. So be careful using that kind of software. You may also be inspired and design some very nice product like this one.
All right, so thank you very much.